So perhaps we could start then the afternoon session of this conference. It's a pleasure to introduce Professor Stefaan Vaes from KU Leuven, who's going to talk about the classification problems in operator algebras.
Okay, thank you very much. So thank you very much for setting up this Zoom conference, this non-commutative conference. It's a great pleasure for me to talk in Ghent while being in Leuven, Belgium, of course. So the kind of mathematics that I would like to present is somehow at the crossroads of, say, non-commutative analysis on the one side, but at the same time there will be a lot of group theory and dynamical systems, and it's a bit at the interaction of both that I'm working. So what is this theme of operator algebras all about? So let me start with giving a very broad and general introduction to some of the even history of the subject. So the kind of topic we are considering is not so much like in some of the earlier talks, single operator theory, but algebras of operators on a Hilbert space. And these algebras of operators on a Hilbert space, we consider them in two distinct flavors. So one flavor connected to the operator norm of an operator, in the sense that the first type of algebras that we are considering are so-called C-star algebras, so the norm-closed star algebras acting on a Hilbert space. And on the other hand, we will meet, and I'm much more involved with that, their measurable counterpart. So if you recall what the weak topology on bounded operators is, namely operators converging weakly if they converge after taking scalar products, then we are interested in those star subalgebras of B of H that are closed for this weak topology. Now, as you may know, and as I will try to put forward in this talk today, is that this whole subject is completely interwoven with group theory, with dynamical systems, more recently also with a lot of quantum information theory, and in the past also strongly motivated by representation theory of both discrete groups and Lie groups. Now, these interactions can already be seen from an analogy, namely the analogy with the classical or commutative case. So one proves that commutative C-star algebras, say unital commutative C-star algebras, they are precisely of the form continuous functions on a compact Hausdorff space. And in that sense, C-star algebra theory is a kind of non-commutative topology. Yeah? So there's a lot of algebraic topology, K-theory, continuous dynamical systems, and then connections with geometric group theory that are going on in this area. On the other hand, commutative von Neumann algebras, they are rather of the form essentially bounded measurable functions on a probability space or on any standard measure space for that matter. And keeping that in mind, you immediately realize that there is a very strong connection with ergodic theory, with measurable dynamical systems, and then with measurable group theory, as I will show during the talk. So the type of questions that we are interested in can be very well illustrated already by specifically considering the operator algebras that are associated with groups. So if you take a countable discrete group G, then there are actually different algebras that one can associate to this object. So first of all, define the left regular unitary representation. So this is a unitary representation of G on the Hilbert space L2 of G of square summable sequences indexed by G. And so we have the canonical orthonormal basis. So all the delta H indexed by the group are orthonormal vectors, and they're just shifted by the group element G, so that lambda G is indeed a unitary operator on little L2 of G. And then we can do a few operations. So first, we can remain on a purely algebraic level and take the linear span, the vector space generated by these unitaries. Now, it's immediately clear that if you multiply two such translation operators, lambda g and lambda h multiplied give you, of course, lambda of gh. So this linear span is indeed a star algebra of operators acting on L2 of g. And as an abstract star algebra, it's not very special. It is the so-called group algebra of the group. You can purely algebraically define it as the vector space with bases indexed by g and with the algebra operation given by multiplication in the group. Now, this group algebra is now not only an abstract star algebra, but it acts on little L2 of g. And this gives you the space to complete the algebra. So you can do it in the topological way by taking the norm closure of that algebra. And this yields the so-called reduced group C-star algebra of the group G. And then you can go one step further, and closing it off in a weaker topology, you can take the weak closure of CG, and this gives you the so-called group von Neumann algebra L of G, still acting on the Hilbert space little L2 of G. Now, it's immediate in this construction that we have this chain of inclusions. So indeed, G, you can really identify G with these unitary elements that belong to the group algebra CG. So indeed, we have a chain of inclusions. And the kind of question we are interested in, and the kind of phenomenon that we are interested in, is that at each of these steps, actually, somehow some of the information of the previous step is wiped out. So at each step, information gets lost, and therefore at each step, there are very natural questions popping up, say rigidity questions, of how much of the information of the previous step is actually retained in specific cases by the next algebra. So why rigidity? I mean, it's rigidity in the spirit of weaker types of isomorphism, automatically implying stronger types of isomorphism. Think of results saying that under this and that circumstance, two manifolds that are homotopic must be isometric, say. I mean, that kind of type of results where you would say, okay, we look at rigidity questions of the style, when these or these C-star algebras of groups are isomorphic, then actually this can only happen because the groups were isomorphic. So that's the kind of questions that come up. Now, in this area, there are lots and lots of famous open problems. So, and let me illustrate them at each of these steps. I mean, so maybe go back at each of the steps, to going to the group algebra, to the C-star algebra, to the group von Neumann algebra. At each of these steps, you have very natural open problems. So on the group algebra level, of course, there is a whole series of wide open conjectures going back to Kaplansky. And let's specifically state them for torsion-free groups, so groups in which every element has infinite order. So one of the famous conjectures is the unit conjecture, saying that in this algebra, the only invertible elements in the algebra are the multiples of group elements. So this is an extremely easy to state conjecture. It's conjectured for arbitrary torsion-free groups, and nevertheless, it has only been proven for like a really tiny class of groups. I mean, there are even very simple torsion-free groups for which it's really wide open. So that's one of these famous conjectures. A slightly less general conjecture is the idempotent conjecture of Kaplansky. And this idempotent conjecture is saying that in this algebra, the only idempotents are 0 and 1. Of course, an idempotent allows you to build invertible elements. So therefore, this is indeed a weaker conjecture than the unit conjecture. But it's one that can be strengthened in another way as well. Namely, what is known as the Kadison-Kaplansky conjecture, the group algebra being contained in the reduced C-star algebra. It's of course stronger to ask that 0 and 1 are the only idempotents in this larger C-star algebra. And now comes an interesting point. This idempotent conjecture seems like a statement that is purely algebraic in nature. It only refers to the group and to this algebraic structure associated to a group. But the cases where we can prove it is actually because we prove statements about sister algebras on the level of sister reduced of G. So these days there are wide families of groups for which the Kadison-Kaplansky conjecture is known to hold. So for those who have heard about the Baum-Kohn conjecture, so those groups for which we can prove the Baum-Kohn conjecture, and we'll meet a few later in the talk, actually the Kadison-Kaplansky conjecture also holds, and therefore the idempotent conjecture holds. A similar thing is not the case for the unit conjecture. I mean, one of the reasons why the unit conjecture has only been proven for really tiny classes of groups is because there hasn't been that kind of link to operator algebras yet. Let's go one step further to the von Neumann algebra level. Probably the most famous open problem on that level is if you take the free groups, so you take the free group with n generators, it's wide open whether or not their von Neumann algebras are isomorphic or not. And it's very fair to say, I think, that Voiculescu's free probability theory has basically been created to approach answers to this question. So Voiculescu has this invariant called free entropy dimension, which has not yet been proven useful to solve this problem. It has been proven useful in many other directions. But there is a whole area of mathematics, actually free probability theory, to approach this question. For a different type of groups, there is a famous conjecture due to Alain Kohn. So contrary to the free group factor problem, where I guess it depends a bit on time whether people conjecture these algebras to be isomorphic or not, for these other groups in the conjecture of Kohn, there is a clear statement that should be true. For instance, if you take groups like SLNZ, so think of this as really lattices in simple Lie groups, then there is a clear conjecture. I mean, the group von Neumann algebras of PSLNZ should only be isomorphic if you have taken the same groups. Actually, there is a bolder conjecture, but that is probably too much and should probably not be true in that generality. The bolder conjecture is, we will meet later in the talk, an abstract, say, harmonic analytic property of groups called Kazhdan's property T. These groups, PSLNZ, have the property T of Kazhdan. And there is a bolder conjecture saying that if you have the group von Neumann algebra of a property T group, then actually the only way that such a group von Neumann algebra can be isomorphic to another group von Neumann algebra is because the groups are isomorphic. And actually, essentially, up to trivialities, the isomorphism must come from an isomorphism of the groups. Yeah, that's the strongest kind of rigidity one can hope for. Okay. Actually, already only stating these open problems, I guess that it's clear that if I throw on the table two von Neumann algebras or two sister algebras, deciding whether or not these are isomorphic can be extremely difficult problems. And on these group von Neumann algebras, I mean, a lot of mystery remains, but there has been a lot of progress, both on the sister side and the von Neumann side, on operator algebras that come with group actions. So now we have seen group von Neumann algebras, group sister algebras. Let's now add to the game some dynamical system. So we will now look at groups that act first of all on topological spaces, so group actions by homeomorphisms of a compact space. They give rise to a so-called cross-product sister algebra. And then measurably, you see the analogy, if you have the action of the group rather by transformations that preserve sets of measure zero, then you can build a cross-product von Neumann algebra. Of course, I'm not going to explain here the detailed construction, but let me give you just the essence. So the main point is that these operator algebras, they really encode the action of the group. So a bit in the same way as the group von Neumann algebra, the group sister algebra encode in a weak way the group, these operator algebras, they encode in a weak way the group acting on the space. So the way in which this happens is because these operator algebras, they contain as a subalgebra in the first case, continuous functions on X, and in the second case, they contain bounded measurable functions on X as subalgebras. But they also contain these unitary elements as we have seen in the group von Neumann algebra. So they also contain a copy of the group as unitary elements. And then the two, of course, they fit nicely together in the sense that they implement the action of the group on the space. So the way the algebraic relation works is that if I conjugate one of these functions on X with a unitary element indexed by G, then this is the same as translating the function by the group action. Okay, so we will focus quite a bit on these operator algebras coming from group actions. And we will see that there is a very interesting kind of dichotomy between so-called amenable groups and amenable actions versus non-amenable. Now, what is amenability? So amenability is a notion that goes all the way back to John von Neumann. Here is the abstract definition, but I will immediately give you examples. So a group is said to be amenable if you can find a finitely additive probability measure on all the subsets of the group that is translation invariant. So there is a way to assign to any subset of the group a weight between 0 and 1. It's only finitely additive, so it's a very non-constructive thing. It's a bit like in Fedor Sukoshev's talk this morning, one of these kind of limit points, like with an ultra limit somewhere, and they are translation invariant. Now, von Neumann had actually a very good reason to introduce the notion. I mean, it was his conceptual explanation to the Banach-Tarski paradox. Yeah? The fact that there is the Banach-Tarski paradox is really because the free groups are not amenable groups. So what are amenable groups? I mean, there are quite a few. The only obvious ones are the finite groups, because if you have a finite group, of course, you can just normalize the counting measure. And then you have, of course, an invariant probability measure on the group. You can show that all abelian groups are amenable. And then there are a few constructions that preserve amenability. So amenability is stable under extensions. It's stable under passage to subgroups. It's stable under direct limits. And this allows you to construct a whole wealth of amenable groups, including, for instance, all solvable groups by taking extensions and so on and so forth. So what are non-amenable groups? First of all, the free groups with at least 2 generators. Since amenability is stable under a passage to subgroups, also groups containing F2 as a subgroup are non-amenable. So once you find in your group 2 elements that satisfy no relation at all between the 2 elements, then your group is non-amenable. Think of all the non-amenable linear groups are like that. So for instance, SL and Z is a non-amenable group. By the way, it has been for a long while an open problem attributed to von Neumann again, whether this is the only obstruction to amenability. But that's now known to be not true. I mean, you can construct non-amenable groups not containing F2. Now, why is there such a huge dichotomy between amenable and non-amenable? On the next slide, I will tell you a bit more on a celebrated theorem of Alain Connes back from 1976. And the corollary says that if you take an amenable group, then actually all these group von Neumann algebras are isomorphic. Although these groups may be very, very different one from the other, their von Neumann algebras are always isomorphic. The whole information on the group is wiped out. Of course, there has to be a little nuance. You can already feel that, for instance, the group being abelian, you can immediately detect on the algebra. I mean, the group is abelian if and only if the algebra is abelian. So that would be a bit silly. So there is an assumption, of course, to be read as infinite conjugacy classes. So the thing is true for all groups where non-trivial elements have an infinite conjugacy class. So in particular, they are not abelian. Okay, so where does this type of result come from? And that will gradually bring me to the heart of the matter of this talk here. I have to introduce a little bit of terminology first. So we have met von Neumann algebras. Let's first introduce a kind of simplicity assumption. So von Neumann algebra is called a factor if you wish, a simple object in a theory if you cannot write it as a direct sum of two. And there is an easy reduction theory going back to von Neumann. Any von Neumann algebra is written in an essentially unique way as a so-called direct integral of factors, a generalized, kind of like continuous direct sum of factors. So again, we meet this infinite conjugacy class assumption. It's straightforward to prove that group von Neumann algebras, they are a factor, even only if this group is sufficiently non-abelian, so has infinite conjugacy classes. And the next notion we have to introduce is to be of type 2-1. So to be of type 2-1 is the same in this kind of infinite dimensional setting as admitting a trace. So it's a functional that satisfies the trace property. It's faithful. So on positive elements, it assigns positive values. And it's normal in the sense of being weakly continuous on the unit ball. Now, it's good to keep in mind that these group von Neumann algebras, for instance, they always have such a trace. On the other hand, as you may feel when seeing this trace property, cross-product von Neumann algebras, they have a trace precisely when you constructed the cross-product from an action with an invariant probability measure. So a G-invariant probability measure is the key property there. So why am I introducing this notion of 2-1 factors? Because really 2-1 factors are like the basic building blocks of arbitrary von Neumann algebras. I have said at the start that arbitrary von Neumann algebras are first of all a generalized direct sum of factors. And then secondly, I mean, this is highly involved, but there is a theory of Tomita Takasaki and again Connes that in a kind of way, I mean, this is oversimplifying things, but in a kind of way, you can reduce the study of arbitrary factors to the study of 2-1 factors. And here is then the famous theorem of Alain Connes saying that all amenable 2-1 factors are isomorphic. Now, of course, I didn't define for you amenability for factors. Maybe I will do it at the very end. I defined it for groups, but there is a notion also for operator algebras. And of course, this is not just an abstract result. There is this one single specific 2-1 factor that they are all isomorphic to, namely the so-called hyperfinite 2-1 factor of Murray and von Neumann. And so what is the hyperfinite 2-1 factor? It's the one that you build out of matrix algebras. So you put 2x2 matrices into 4x4 by putting two blocks, and then 4x4 in 8x8, and you take a direct limit, you take the appropriate completion, and this is the so-called hyperfinite 2-1 factor. And the big breakthrough result of Connes is that all amenable 2-1 factors are isomorphic to this specific R. And then, I mean, moreover, he, and then also in work of Haagerup, actually all amenable factors have been completely classified. But it would be a bit too involved here to explain how exactly they are classified. But amenable factors, amenable von Neumann algebras, they are completely classified. Okay, so my work is then, of course, going beyond this amenable case. And I want to illustrate this with a few of the, say, prototype results that mainly in collaboration with Sorin Popa and using his so-called deformation rigidity theory, the prototype of classification results that we have proven beyond amenability. And a very good illustration, I think, is by looking at Bernoulli actions. So what is the Bernoulli action? The Bernoulli action of a group G is a very concrete probability measure preserving action where you take a base space, X0, and then you take an infinite product indexed by the group, and you shift, you translate in this way. So this is a nice probability measure preserving action. It is so-called ergodic. So the cross product is a 2-1 factor. By Connes' celebrated theorem, if I perform this construction with any infinite amenable group, any infinite abelian group, whatever, you always get isomorphism with one and the same 2-1 factor, namely the hyperfinite 2-1 factor. On the other hand, and that's the kind of rigidity result we are after, for other types of groups, a completely opposite phenomenon arises. For instance, if G has Kazhdan's property T, like as LNZ, or also if G is a direct product of two non-amenable groups, then, for instance, exactly the opposite happens. It's no longer true that all the cross products tend to be isomorphic. No, they exactly remember the group and the action, in the sense that whenever such a cross product is isomorphic with another cross product, the only reason is because you took the same group and you took the same action. So that's a first sample result of the kind of superrigidity phenomena that we obtain. Another nice illustration is, I think, for the free groups. So I explained to you that it's wide open whether the group von Neumann algebras of the free groups are isomorphic if you take a different number of generators. Although, on the other hand, what we could prove with Sorin Popa is that if you take cross products and you can take them with any action, any ergodic action, probability measure preserving of these free groups, when you took a different number of generators, you always get non-isomorphic von Neumann algebras. The reason for this is that there is a result in the background, namely any isomorphism you may have between two such cross products must, up to trivial modifications, automatically preserve these canonical abelian subalgebras, these L-infinity subalgebras. These are so-called Cartan subalgebras, and what we really prove is a uniqueness theorem for Cartan subalgebras in such von Neumann algebras. Now, what is so special for an isomorphism preserving these canonical subalgebras? This brings us a bit back to ergodic theory, because since pi is mapping L infinity of x onto L infinity of y, this pi is inducing a map from x to y. And this map from x to y is a so-called orbit equivalence. It's not yet a conjugacy of the actions, it definitely need not be, but delta must map orbits to orbits almost everywhere. And that brings us to so-called measurable group theory. Measurable group theory is actually this kind of thing, looking at how group actions, partition the space into orbits. And there is a very remarkable result of Damien Gaboriau saying that L2 Betty numbers of a group are preserved under this weak notion of orbit equivalence. And the L2 Betty number, the first L2 Betty number of the free group is n-1. So indeed, you do get the number of generators as an invariant. Now, the reason why I picked out this kind of specific theorem here is not only because it's nice to state, but also because I want to make this final connection to L2 Betty numbers, because that's another area where actually operator algebras have really served another area of mathematics. I mean, L2 invariants are now all over the place in geometry, algebraic topology, and so on. And I want to end this talk by quickly saying what these L2 Betty numbers are, and then by saying what they might become for 2-1 factors in the long run. So it's, of course, there is first of all a homology or a cohomology theory in the back. So take any group G, and then you take the Hilbert space L2G, which you can view, of course, as a left G module by left translation. But it's also a right module, say, on the group von Neumann algebra, because you also have right translations. As a consequence, if you take just Hochschild cohomology of the group G with coefficients in this G module L2 of G, since this left G action and the right LG action commute, this Hochschild cohomology, a priori just a vector space, this Hochschild cohomology space is also an L of G module. And now the whole theory of traces on 2-1 factors allows you to define a dimension, not just vector space dimension, but dimension relative to this L of G action. Of course, I cannot define you here what this kind of LG dimension is, but taking this LG dimension, you get exactly the end L2 Betty number as defined by Attia, by Chigr-Gromov, and then Wolfgang Lück in this kind of generality. And is one of the very rare invariants of groups that are stable under orbit equivalence. And this allows me to end with the conjecture and with a big dream. So one conjecture stated by many people is that actually, if you take cross products, any cross product of any group, then actually the L2 Betty numbers of the group are an invariant of the 2-1 factor. We did prove that for quite a few groups, like hyperbolic groups, including free groups then, of course, but not in general, by no means. And then the big dream to end with is that actually many people would like to define a kind of L2 invariance for not cross products and recovering this, because we are maybe getting closer and closer to this, but defining L2 invariance directly for 2-1 factors. And then the big dream is, of course, that you get this formula. But this is way out of reach at the moment. Okay, thank you very much.
Thank you very much for your talk. Are there any questions?
I have one question, if I may.
Yes, please.
Okay, Professor Vaes, maybe my question is, maybe it not make sense, but I will try, yes? Free groups are not amenable groups, yes? Like the case of the—
That's right.
Yes, the group 2 generators is not amenable.
Yes.
But this is the reason, or this is because of the Banach-Tarski theorem, yes?
Yes, that's more or less true what you say. I mean, if, for instance, there is no Banach-Tarski theorem for the disk. So if you take in 2 dimensions the disk, it's not possible to cut the disk in a finite number of pieces, move these pieces around and get 2 equally sized disks. And the reason is because the isometry group of R2 is an amenable group. And you can transfer this invariant mean to like a measure to weigh the disk, and therefore there is a contradiction. I mean, you cannot get weight 1 and then weight 2. But the isometry group of R3 is non-amenable, so there is no way to have this like everywhere defined on all subsets weight of the disk, of the ball, I mean. Sorry.
But in the case of 3 dimension, one can prove that one can split the sphere between 2 balls with the same measure, yes?
Yes.
It's Banach-Tarski, I don't remind the
Banach-Tarski paradox, yes.
Paradox, yes. But this is because of the axiom of choice, yes?
Of course.
But then existence of not amenable groups is consequence also of axiom of choice.
No. The fact that the free group is non-amenable, of course, I mean, how much of function analysis one does without the axiom of choice? I mean, that's a difficult question, but in principle, you prove non-amenability of F2 in a constructive way.
Okay. This is my first question, but other question that I have is just one. Okay, I will try also. Is you talk about the Betty numbers, yes? Betty
yes.
numbers. I remember from my basic courses that with Betty numbers, one can have one identity for the Euler characteristic. Yes.
Yes, it still goes through here.
Ah, okay. Thank you very much.
Yes, but you have to, of course, take the things in the right way. So here I had L2 Betty numbers for groups. So the whole story would be you start with the compact manifold, you have the fundamental group, and then there is a way the fundamental group is acting on the covering space, and then you do associate L2 invariance to that setting, and then there is a formula for the Euler characteristic.
Thank you very much. Thank you.
Can I ask?
Yes, please.
Didn't you promise to define amenable Banach algebras and give Johnson's theorem?
I didn't mention Johnson. I did promise something if I would have 5 minutes left, which I did not have, but it's here if you wish.
Well, it's a wonderful talk. After 10 years, ICM Hyderabad, I heard you.
Oh, thank you. Yes, I remember. Yeah, that's right.
Yes, wonderful talk. Wonderful talk.
Thank you.
I would have, is it possible to hear me?
Yes.
Yeah. Okay. I would like to ask you something about groupoids. So on one hand, groupoids are much more general than dynamical systems. On the other hand, there are a lot of C-star algebras which have a groupoid model, especially if you admit twisting by two cocycles. It seems that a certain rather large class can be represented in such a way. In addition, for groupoids, some parts of your talk are possible, well, let's say including Cartan algebras or orbit equivalents. A lot of the vocabulary is possible for groupoids. So I suppose, I guess, but please tell me if I'm true, that such stuff can be done for groupoid C-star algebras and groupoid von Neumann algebras.
So the distinction, the short answer is yes, a lot can be done and a lot has been done, but there is a huge distinction between the continuous topological C-star side and the von Neumann algebra side. So measurable groupoids, they tend to trivialize way more than continuous groupoids are. So there are much less intricacies of all kind of levels, in the sense that on the von Neumann side, I mean, it's essentially equivalence relations and group actions, and a lot can be said and a lot goes through. On the topological side, though, even defining what is orbit equivalence requires care. I mean, there are different versions of how much continuity you require, and this kind of strong theorems deducing isomorphism of groupoids out of isomorphism of C-star algebras and so on, we don't have that yet, yeah? But it does play a more and more important role in the classification theory of nuclear C-star algebras.
Oh, I see. So the groupoid C-star algebra is rich enough. The von Neumann version is not so promising from this point of view.
Well, in the sense that the main problems on the von Neumann side are either on the level of group von Neumann algebras or on the level of equivalence relations. So somehow say either principal groupoids, measurable groupoids, or just groups. And both have interesting phenomena as much as you want, but then somehow interpolating between the two and looking at groupoids is a bit less interesting.
I see. Thank you very much.
Are there any other questions?
Yes,
please.
I also have a question.
Sorry.
In the beginning, in your hierarchy of algebras, group algebra, reduced C-star algebra, von Neumann algebra, you omitted the full C-star algebra. Any special reason for that?
No. Yeah, there is no special reason. Of course, it would not appear in the inclusion hierarchy. I mean, it's an algebra that's, say, above C-star reduced, and C-star reduced is a quotient of this algebra. Mm-hmm. And it does not have a clear von Neumann algebra counterpart. But there is definitely no reason to not consider it, and it has been considered, and there are many interesting results.
Oh, okay. Thank you.
Any other questions?
Alessio, can I ask a question?
Please do.
Yes. Is it possible to relate these Betti numbers to the context of weak Morse inequalities, where one classically gets on the number of critical points of a Morse function on a Riemannian manifold, a lower bound on the number of them using these Betti numbers? So is such a concept possible to generalize it to this context?
But that is for, I guess, the, say, ordinary Betti numbers, where it's really dimension of a homology or cohomology theory, yeah? Right. Vector space dimension. I don't know of any variant of that on the L2 level. I wouldn't know.
Mm-hmm. Okay.
Any further questions? Well, if not, I think we can thank Professor Vaes again for his very beautiful talk. And I think perhaps we could see if, Professor Montoyo, if you could share your screen.